All right, today we're going to talk about infinite series. An infinite series is simply the sum of an infinite series. So we have a sub 1 plus a sub 2 plus these are all the elements, all the way up to a sub n, and then to infinity. It keeps on going. So it's just some of those. So what we're going to try to do here is how to measure these, how to find the summations of all these using calculus to speed up the whole process. Yeah, obviously, adding up all these will be too difficult to do. So what we're going to look at is trying to find some formulas that we can use to make it easier for us. All right. All right. Now, so since these are our elements, are our sequence of numbers, the sum, which is the partial sum of S1 is just A1, of S2 is A1 plus A2. S5 is A1 plus A2 plus A3. All right, so these are our partial sums. Eventually, what we're trying to get to is being able to sum up our n terms. So in order to do that, when we have a series of numbers, what we have to do is try to look for patterns. All right, so once we find a pattern, then we can apply these the rules that we're going to be showing here. Now, when it comes to series and sequences, we have two types. We have arithmetic sequence or series. Arithmetic sequence are when the numbers are connected by a common difference. So we just say common difference is because if we have a series of numbers, and so forth, A2 minus A1 will give us a number. It'll be the same number as A3 minus A2, which will be the same difference as A4 minus A3. So the difference between each of these are going to be the same. So that means in order to go from A1 to A2, I add some number. It'll be the same number I add for all of these. That's arithmetic sequence. And then we have a geometric sequence or series. When the numbers have a common ratio. So the common difference is simply an plus 1 minus an. Common ratio is an sub 1 over an. That's the ratio. This is the difference. That's the ratio. And it'll be important for us to find that common ratio in order to start solving all of these. All right. In the in the summation of all these, if we were to add up so I said we had A1, it's S1 is equal to A1, and so Sn equals A1 plus A2 all the way up to A sub n. Again, once we find a formula for this, then we can write it as a summation of something. Now, if the series converges, if the series converges, it equals some number, some limit number. A finite number. If not, then it diverges. In other words, if it doesn't equal some, the summation doesn't equal some number, then we have a divergent sequence. First, this is the arithmetic sequence. They're all, if it follows this, then they're all some sort of pattern. So let's look at geometric series. Remember, we have a common ratio. We'll call that R. And we also have the beginning term. So we'll also have a beginning term. The geometric series can be represented as this. A and then you keep on going. Remember, in order to have a common ratio, this R is a fraction. To go from here to here, I have to multiply it by the ratio. To go from here to here, I have to multiply it. The geometric, the arithmetic sequence is you add, but for the geometric, we multiply. So we multiply by R, we multiply by R, we multiply by R, and so each time. So that's where we have our formula is going to be the summation of A, R, n minus 1, where n equals 1 to infinity. This is a geometric series. All right, so that's what we're going to be looking at in this first part. So the nth partial sum. Remember the arithmetic sequence, we had the partial sums were like this. So now with the geometric series, S1 would be A, S2 would be A plus AR, S3 is A plus AR squared, and also and so forth, A plus AR squared, all the way to ARn minus 1. The reason it's n minus 1, because we have to have n number of sequences. This is the first one, the second, and so forth. All right. So now we're going to look at a way to determine if this sequence, the sum of the sequences, if it converges or diverges. All right. So since the first term is a constant term, let's look at if we multiplied the same sequence by the ratio. So we have AR plus AR squared plus AR cubed all the way to ARN, because the n minus 1, we multiplied with this one. So the 1 from this one minus 1, so it just equals R to the power n. So now, let's find the difference between these two. So we have Sn minus R of Sn, which is equal to Sn, we factor it out, 1 minus R. If we subtract this minus this, what we're going to get is, okay, we have the first term, because nothing cancels with it. Now, these cancel, because these will be minuses. So these are all changed negative. So that cancels, that cancels, that cancels. So we have all the way up to AR to the power n, which is A1 minus R to the n. To solve for this, the summation of the sequence, we divide both sides by 1 minus R. Again, as long as R, the ratio is not equal to 1, we're good to go. Bring out space there. So we have our summation. Sn 1 minus Rn over 1 minus R. R cannot equal 1 because it'll make it undefined. So now, if R is less than 1, R can be positive or negative, so we'll look at the absolute value of R. If it's less than 1, if it's a fraction, then S of n converges to a number. So if the absolute value of R is less than 1, then this equation boils down to that. The reason being is because as R gets smaller and smaller and smaller, this one disappears faster. So we have this one left over on the bottom. Oh, that leads us to our first formula. Remember, all this stuff, we have S of n, which is the summation as n goes from 1 to infinity of AR n minus 1. That equals our formula here, A 1 minus R, whenever the absolute value of R is less than 1. So conversely, if it's less than 1, it converges. If it's greater than or equal to 1, it diverges. All right, so let's look at our examples. Example 1. Find the geometric series with A equals 1/9, and the common ratio is 1/3. All right. So where we just plug in those values into the equation, and then let's go with it. See what happens. This is the formula we'll be using. So we use the summation, because we're looking for the sum, just the sum of the sequence. A to R n minus 1 from n equals 1 to infinity. So we have A is 1/9 and R is 1/3. So that's this part. It equals that. This equals A1 minus R. So A is 1/9. 1 minus R is 1/3. 1/9. 3/3 minus 1/3 makes it 2/3. Take the top, leave it alone, flip the bottom. 3 and the 9 cancel. 1 times 1 is 1, 3 times 2 is 6. And there's our sum of the sequence. So we're using this formula here. It's a summation of all of the sequence series. Example 2. Go ahead and write down because I have the example sheet for you all. Example 2. The series n equals 0 to infinity, 4 to the power n, negative 1 to the power n times 5. So when n is 0, that's 1, that's 1, so we just have 5. Now when n is 1, then we have a negative, it would be minus 5/4. When n is 2, that's squared, so it's positive. So it's positive 5/16. When n, this is when n equals 0, 1, 2, 3. So when n equals 3, that makes it a negative. 4 to the third is 64. So it's going to alternate from this positive, negative, positive, negative, positive, negative. All right. It says the series is geometric. Yeah, because it's multiplied. So what would A equal? And then what would R equal? And then one knows converges to what value? So these are the ones we have to fill in. So what we have on top, remember the formula we're looking for is the summation of AR n minus 1 equals A1 minus R. That's the formula we'll be using. Since all these are, so the top number is our A. And what's our ratio? So what this is, if that's A, then our ratio is negative 1 to power n, 4 to power n, which is negative 1/4 to the power n. So it's negative 1/4. Since we have these, we can see where it converges to. Negative 1/4. 1 plus 1/4. So this is 4/4, makes it 5/4, 5/1, 4/5. It converges to the number 4. All right. Let's look at example 3. Example 3 looks like this. You drop a ball from A meters above the flat surface. So that's where you drop it off. Each time the ball hits the surface after falling a distance of h meters, those are meters, it rebounds a distance of RH, where R is the positive but less than 1. Because if it was greater than 1, it would increase. It wouldn't. This is a decreasing sequence. Find the total distance the ball traveled up and down. So we'll know from here till it stops bouncing. All right, so let's start. What do we know from this question so far? We're looking for the total distance from drop to stop. So according to our graph here, we have this plus this plus this plus this. So it's AR squared, R cubed. So we know that the sequence is going to be A plus AR plus AR squared plus AR cubed, and so on and so forth. But this is AR. This is also AR, so it goes in there twice. This is just, and this one only travels down, so it's S equals A plus 2AR plus 2AR squared plus 2AR cubed, and so on and so forth. So the sum of these, that's the original one. If we add up all these, we got 2AR. Remember, it's A 1 minus R. So it's 2AR over 1 minus R. Okay. Because that's the sum of all these. Just get a common denominator. So we have A 1 minus R plus 2AR over 1 minus R. A minus AR plus 2AR over 1 minus R. One negative 1 AR plus 2 AR is a positive 1 AR. On the top, we can factor out. So that's going to be our formula. Okay, what else did it tell us? What's we have to figure out now? We have to figure out from here, which this is it. We have to figure out what A is and what R is. Well, not telling us. This is just a general formula. So let's say A is 6 meters, and our bounce each time is 2/3. Let's say that we have these. So if our initial bounce dropped from 6 meters and our common ratio is 2/3, what is this formula? 6, 1 plus 2/3, 1 minus 2/3. This is 3/3. So we have 5/3. 3/3 minus is 1/3. So it's 3/3 minus 2/3. So the 6 and the 3 cancel. So we have 10 up on top. So it's 10/1 times 3/1, which is 30 meters. So the ball would have traveled 30 meters after bouncing up and down, up and down, up and down, up and down, 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 down. Where's my example sheet? Where's my example? Oh, there's it. All right. So example 4. Express the repeating decimal 5.232323 as a ratio of 2 integers. Example 4. So express 5.232323, so it repeats itself. Ratio of 2 integers. Okay, so 5.232323 is actually the 5 plus this decimal, which is 23/100. Since they're in groups of 2, this is 23, this is 100, this is 100 squared, which is 10,000. And this one is going to be 100 to the third, and so on and so forth. Because they're in groups of 2. This is tenths, hundredths, 1,000ths, 10,000ths. So that's what these are, and so on and so forth. All right, so we have, from here, we have our initial value. All of these are terms of 23/100. So we can see what this sum is going to be. So we factor out 23 over 100, we get 1 plus 1 over 100. This one's going to be 1 over 100 squared, and so on and so forth. So with this, we see our sequence. The ratio is 1 over 100. A is 1, and the ratio is 1 over 100. Then it just keeps on going the same all the entire time. So what we have here is 5 plus 23 over 100. And this whole sequence is A over 1 minus R, which is 1 over 1 minus 1 over 100, which is 99 over 100, which is 1 over 0.99. This is just the bottom. 0.99 is the bottom. So multiply these two together. 23 times 1 is 23. 100 times 0.99 is 99. Get a common denominator. It's 99. So it's all over 99. So 45 plus 45 plus 4 is 49. Plus 23. Eight, 1, 5. Yeah, so we have to find the A and the common ratio, which is this. So this one's common with everybody. 23 over 100. This is what we're left with. Now each of these have a 1 in common. 1 over 100. The ratio is 1 over 100. Each one of these are times 1. All right, that one looks pretty good. That's example 4. Example 5. Example 5. Find the sum of the telescoping series, one, blah, 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 all that stuff. Okay. Why is this one called a telescoping sequence? Is because what we see what it's doing is if n is negative or is positive, it'll just increasingly keep on either increasing or decreasing. All right, so this is what we have to look for. Find the sum of the sequence. So the sequence is this, 1 over n. We have to use partial sums. And since the numerators are a constant, it's 1, A and B both have to equal 1. So this breaks down into 1 over n plus 1 over n plus 1. So now we know what we break down into smaller ones. Why is that important? Because now, if we're going to find our series from n equals 1 to infinity, or some value n, doesn't matter what size it's going to be. I'll say keep going to infinity. So we have 1 over n plus 1. It equals this. So this is the same thing as summation of n equals 1 to infinity of 1 over n plus the summation of n equals 1 to infinity of n plus 1. So let's look at the sum of these. When n is 1, the sum. When n is 1, this is going to be 1. This is going to be 1/2. Ah, that's where I messed up. Yes. I should have solved A and B. Right. Okay, so when n is 1, we have this. Summation when n is 2, which is 1 over 3. When n is 3. When n is 4. Keep on going. So we notice if we dropped all the parentheses, those are all leading terms. This 1/2 and that 1/2 cancels. This 1/3 and that 1/3, that 1/4, and so on and so forth. So we're going to end up with the first one, since all which will be left with is the very last term, and that's going to be 1 over n plus 1. So the limit as n goes to infinity, 1 stays the same. This number goes to 0. So we're saying this the sum of all this stuff equals 1. Yeah, I should have worked this one out with the partial sums. Okay. This is 2, no, this is page 3, and this is page 4, so I don't use all these. Okay, the next part we're going to talk about is the nth term test for divergence. Divergence. So we'll look at this as an example. So it diverges. For example, e to the x as x goes to infinity diverges because the graph keeps on going higher. It doesn't become small. E to the negative x, on the other hand, as x goes to infinity, converges because it gets on smaller, 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 smaller. So it all depends on what your values are. So we're looking at the series n equals 1 to infinity of n plus 1 over n. Numbers increase, diverges, or decrease, converges, as n goes to infinity. So when n is 1, we have 2 over 1. When n is 2, we have 3 over 2. When it is 3, we have 4 over 3, 5 over 4, 6 over 5. It keeps on going. It's 1.5, 1/3, 1/4. So as we keep on adding, each successive addition is larger than the one before. So in other words, this partial sum of 1 is 2. Two plus 1.5 plus 1.3. It's 4.8. So each successive one is larger than the previous one. So it's keep on going. Eventually, as we go to infinity, it goes to infinity. The sum goes to infinity. Okay, that's what that shows, the nth term tests for the divergence. So as we keep on going, n plus 1 over n. Basically, we saw it's going to diverge because from algebra, when we looked for the horizontal asymptote, if you had a sequence like this, what we would do is we would divide the largest exponent is n to the first. So divide each of these by n. 1, n over n is 1, 1 over n over 1. So it's 1 plus 1 over n. As n goes to infinity, this one goes to 0. Since this is not 0, it diverges. Which we're going to show next is the limit as n goes to infinity of our sequence must equal 0. If this sequence converges. Since it didn't equal 0, the limit of it, it diverges, which is what theorem 7 says. If the summation of our sequence as n goes from 1 to infinity converges, then the limit of our sequence goes to 0. Note, The opposite may not be true. Just because a sequence goes to zero doesn't mean it converges. So this is the only theorem we have. If the summation converges, then the limit of the series goes to zero. So as it says, the nth term test for divergence is this. This diverges if the limit as n goes to infinity of a sub n fails to exist or is not zero. So that's the nth term divergence. So once we see sequence, if the limit of the sequence goes to zero, then it converges. If not, it diverges. And that's a shortcut method instead of going through the whole stuff, everything we've been doing earlier. Okay, so example 7. Example 7 has a whole series of examples. So A, the summation as n goes from 1 to infinity of n squared. So does it converge or diverge? So as n goes to infinity, what happens with this? So remember, our a sub n is n squared. As n goes to infinity, this one goes to infinity, so it diverges. There's n squared as n goes to infinity, that goes to infinity even faster. The second one, the summation as n goes from 1 to infinity of n plus 1 over n, which we figured out earlier. Remember, as n goes to infinity, so we divide each of these by n. There's 1 plus 1 over n over 1. As n goes to infinity, this one goes to 0, this equals 1, so it diverges. It doesn't equal 0. The summation as n equals 1 to infinity of negative 1 n plus 1. So let's look at this. So the first one, when n is 1, it's going to be positive 1 because 1 plus 1 is 2, negative 1 squared is 1. Next one's positive 1. Next one's negative 1. Negative 1, positive 1, negative 1. This one diverges because the limit of negative 1 n plus 1 as n goes to infinity does not exist. It alternates, positive 1, negative 1. N equals 1 to infinity of negative n to n plus 5. So let's see what happens. This is a sub n, so we take the limit as n goes to infinity of negative n to n plus 5. Divide each of these by n. So the limit as n goes to infinity of -1 over 2 plus 5 over n. This one goes to 0 as n goes to infinity. So the answer is -1/2. So it diverges. Doesn't equal 0. All right, where's my next page? Examples. This is page 5. Example 8. The series, well, this is not really an example, but if we had the series 1 plus 1/2 plus 1/2 plus 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/8 plus 1/8 plus 1/8 plus 1/8 before. And so on and so forth. You see how each of these series, if we add them all together, they equal 1. So it's 1 plus 1 plus 1. So it keeps on going. So this thing diverges. It's the sequence of this function is 1 over 2 to the power n. It diverges because it keeps on going to infinity. Each one of those add up to 1. So you have 1 plus 1 plus 1 plus 1, infinite number of times. Okay. The next section is dealing with combining series. This. Whenever you have two convergent series, we can add them by terms or subtract, add, subtract, multiply, divide, or not divide. We can do the basic operations to them. So if you have two convergent series, summation of A equals capital A, summation of B equals capital B. If I have summation of A plus B, I can split those up. Summation of A plus summation of B, which is capital A plus capital B. I have the same with the difference. I can split them up to summation of A minus summation of B, which is capital A minus capital B. Or if I have a constant multiple, that constant goes in front. Summation of A is capital A, so it's K times A. Okay, this is also an important comment. The summation, A and B are both convergent. But what if they were both divergent? In other words, if summation of A equals 1, it is 1 plus 1 plus 1 plus 1 goes to infinity, and summation of B goes to -1 plus minus 1 minus 1 goes to negative infinity. So together, all the positive ones and negative ones cancel out, so we get 0, 0, 0. So if they were both divergent, they can converge if we put them together. All right, so that's a pretty important distinguishing fact that we have to put, that it's doesn't just because it's divergent each one separately, we can put one when we put them together, we'll get a, if they're both divergent, we put them together, we have a converging sequence. All right, so let's look at example 9. Find the sum of the following series. A. Summation as n goes to 1 to infinity of 6 n minus 1 3n minus 1 minus 1. All right. So remember, we're using the combining series. This one, since it's monomial on the bottom, we can split these up. Now we can split those up even further. So this becomes 3 over 6 to the power n minus 1. This is the same powers. This one is 1 over 6 to the n minus 1. Makes this one 1/2. Makes this one 1/2. All right. We put those on the bottom. This first one, it's 1 over 2. And the second one, it's 1 over 6. Since we have these, we can now put them in our formula. A is 1 minus r. A is 1 minus r. Six over 6, so it's 5 over 6. One over 1 is 2. This is 6 over 5. Which is 10 over 5 minus 6 over 5, which is 4 over 5. It's A. Let's look at B. Summation as n goes to 0 to infinity, 4 over. So this is example 9b. N goes from 0 to infinity, 4, 2 to the power n. You notice, so if we start at 1, we go to n minus 1. If we start at 0, we go to n. This is the constant, so we take it out in front. Now we could figure out what A and R, figure out this one. A is 1, R is 2. Because this is the same thing as 1 over 2 to the power n. So this is R to the power n. Again, we use our formula. to go from here to here. So we have 4 times a is 1, 1 minus not 2, it's 1/2. One minus 1/2 is 1/2. 1 divided by 1/2 is 2. So the answer is 8. All right. Adding or deleting terms. We can add finite number of terms to a series or delete a finite number of terms without the series changing convergences or divergences. Okay, in this case, we usually change the sum from n equals 1 to that. If we add, let's say, 4, we start with that. So now what this means is, with our series here, let's look at this one. It starts at 1 to infinity. So we can that's going to go forever. But if we want to stop at 4 and have another series, these first sequence of series terms aren't going to do too much. It doesn't affect the convergence or divergence. What affects what happens further on down. So now we have this one. We start off at 4, go to infinity. This is n equals 1, n equals 2, n equals 3. This equals n equals 4 to infinity. So we can rewrite that the same way, as we know that this is from 1 to infinity. If we subtract the first 3 terms, then we have this last term. All algebraic, actually. If you look at it, if we're solving for this term, we'd have this, and we move each of these over, which is what's happening here. So if we don't start off at 1 or 0, then if we start off at 1, that goes to n minus 1. If it goes to 0, it goes to n. So that introduces us to what's called reindexing. So originally we go from n equals 1 to infinity, but if we're going to add increase like we have above 4, we added 3, then we have to subtract it from our sequence. If we go from 1 and we subtract it, then we have to add it to our sequence. So, like, for example, here in example 10, the sequence we have is n equals 1 to infinity of 1 over 2 n minus 1. Sorry. If we start off at 0, because we start off at 1, so we subtracted 1 here. That means we have to add 1 there. So it goes to 1 over 2 to the power n. We subtract 1 here, we add 1 there. Let's say we want to start at 5. So from 1 to 5, we added 4, which means here we have to subtract 4. One over 2 to the power n minus 5. And the last one, I want to go to -4. So from 1 to go to -4, I subtracted 5 here, so I have to add 5 here. So n minus 1 plus 5 is n plus 4. So it's whatever you shift, you reindex your beginning point. If you from the basic standard, n. I'm going from 1 to 6. I added 5. Since I added 5 down here, I gotta subtract 5 up there. So I'm going from 1 to negative 4. So here I subtracted 5. 1 minus 5 gives me negative 4. Since I subtracted 5 here, I have to add 5 here. These have to be opposites. They have to negate what you just did. There we have it. That's chapter 10, section 2. Good luck, everybody. Happy Thanksgiving. And I'll see you all next week.